All right, so yesterday we started chapter 17. One thing I will warn you guys on, tomorrow's lecture is an important lecture to attend. If you do not attend tomorrow's lecture, the next section may not make a lot of sense, so please come tomorrow. We are going to spend the next chapter talking about conjugated pi systems, and we said that conjugated systems are where you have adjacent double, single bonds that are all lined up, and you run into these unique resonance structure situations. So, for example, the one on the left is conjugated because we can move the pi bonds around, but the one on the right is isolated because we cannot move that alkene anywhere. And then we said that when you look at the molecular orbitals for conjugated pi systems, you've got all of these p orbitals kind of sticking up and they're aligned, which allows for pi bonding to occur. But the next door p orbitals also have a slight amount of overlap, and so that carbon-carbon bond that we traditionally show as a single bond does have some double bond-like character, which means these conjugated systems are actually a little bit more challenging to rotate than a traditional single bond. What we're going to do today is we're going to take a look at the preparation of these and then the molecular orbital picture and a handful of new reactions. So let's go to the preparation of diamines. I'm going to throw up a reagent, and I want you guys to help me predict what base we need in order to give us this conjugated diene. What do you think? Yeah, exactly. So in this case, terbutoxide might be a good one. So I'll abbreviate that TBU-OK. And is this E1 or E2 elimination? E2. It's a very strong base, right? Strong bases always favor E2 elimination. So it's pretty simple to make these just through elimination reactions. What about if we want to make the same diene from this dihalide? Can I use something like sodium hydride? Why not? Yeah, remember, if we use a small base, we would end up forming our double bond in the more substituted position. We don't want the double bond in the more substituted position. We want it in the least substituted positions. So we need to use a strong, bulky base again to give us our Hofmann product. And both of these are through E2 chemistry. Pretty easy, pretty straightforward. It's just reviewing old chemistry from first term. Does that make sense? All right, now the kind of crazy part. We're going to look at the molecular orbital theory. And I know these pictures are a little bit complicated. You're more than welcome to copy them down as best as you can, or you can just look in your book. We said that with a conjugated system, we normally represent it with these pi bonds going in between adjacent carbons, and you've got that single bond between those two internal carbons. However, that's only one molecular orbital. So if we look at this compound, and I'll redraw it over here, the compound shown is this diene. We actually have a bunch of molecular orbitals. If you look at the one on the bottom, what this means is that all of the lobes are in phase. What does it mean when a lobe's in phase?
Phased together.
Yeah, it's phased together. They constructively overlap. So in this case, all of these p orbitals down on the bottom share the same lobe in that blue area, right? If we go up to one molecular orbital higher in energy, we end up with this pi bond overlap between two side carbons, and then a pi bond overlap between the other two carbons. So that's our traditional way of viewing these molecules, is by viewing this molecular orbital. This molecular orbital is called the highest occupied. Does occupied have two P's or one? I'm having a brain freeze. One. This is the highest occupied molecular orbital for this diene. Oftentimes that's a mouthful, so instead of calling it the highest occupied molecular orbital, people will just simply refer to it as the HOMO. So both of these are the same representation. Anytime you have a phase change between one lobe being in line and another lobe being flipped, we call that a node. So you can see in our highest occupied molecular orbital, we have one node going in between the two internal carbons, and that just shows that those p orbitals don't constructively overlap with one another anymore. All right, if we go up, we've got these other lobes. The next one, we've got two nodes in between it. And as you guys can see, in this one, the internal two carbons, right here, I guess that's a little bit hard to see, right here and right here, now they're overlapping. That kind of gets to the point where I was making, where I was saying that internal carbon-carbon bond right here actually has a little bit of pi bond character, right? Because those orbitals can overlap if they're in the right phase. So in this case, this is your lowest unoccupied molecular orbital. Unoccupied molecular orbital. The acronym for this is going to be called what then? LUMO. Oftentimes chemists are really interested in this HOMO-LUMO gap or frontier molecular orbital theory because these electrons in this HOMO orbital can be excited up into the LUMO orbital. So for example, you could knock one of these red electrons up into this orbital, and then what do you think happens if we stop exciting it? Yeah, it'll relax back down and release energy. So oftentimes spectroscopy utilizes this phenomenon where we excite an electron from our HOMO orbital all the way up to our LUMO orbital, and then it can relax back down. When it relaxes back down, there's a few different ways that can occur. That electron in our LUMO orbital can relax back down and release heat. It can release a photon. So if you guys have ever seen fluorescent molecules that glow under a black light, that's exactly what's happening. You're taking a black light, you're exciting one of the electrons from the HOMO into the LUMO orbital, and then when it relaxes back down, it emits a photon back towards your eyes. So this is really important. The other thing you notice too is if you count the number of potential nodes that we have, we've got 4 electrons in our pi system, our conjugated pi system, which means we're always going to get 3 possible node configurations, one with no nodes, one with 1 node, one with 2 nodes, and one with 3 nodes. So you end up with this statistical distribution where you rank them from lowest or most stable energy landscape to least stable energy landscape where you've got no overlap. All right, let's take a look at a more complicated system. Oh man, let's see if I can get this to fit. This one's a little bit harder to see. But let's take a look at the diene shown here. Right, we've got 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. So this is the molecule we're representing with this energy diagram. Which ones are HOMO? Is it going to be the bottom one, the second one, third one, fourth one, fifth one, or sixth one up? Yeah, the 2-node one. So if we look at this one, this is going to be our HOMO, or our highest occupied molecular orbital, because that's the highest energy orbital that still contains electrons in it. And then if we look at our LUMO, it's going to be the one right above it. One interesting thing is that the more conjugation you have in your system, the smaller this HOMO-LUMO gap becomes. So if we were to add on even more and more double single bond alternations onto the end of this, that gap would begin to shrink smaller and smaller and smaller, which means it would take less energy to excite an electron from that HOMO band into the LUMO band. And we talked a little bit about that when we were looking at spectroscopy, UV-Vis spectroscopy with beta carotene. You guys remember I said the more double bonds you add, the more red-shifted it becomes, which is why beta-carotene shows up as orange. If we were to cut off some of those double bonds, it would shift more into that blue region. So in this case, it's in the red region because it absorbs relatively low energy red light because it's got so many alternating double single bonds. The book goes into this in a fair amount of detail. You're more than welcome to read up on it. It explains kind of the physical phenomenon behind conjugated systems. But what I really wanted to get into in this chapter are the reactions, because they're synthetically useful and we're going to use them a lot. So the reaction we're going to learn today is electrophilic addition. But most of you guys might even know how to do this without having learned it. I'm going to give you guys a problem, and I want to give you guys a few minutes to process what your answer might be for this. So we've got this conjugated diene, and we're going to react it with HBr, and I'm going to tell you guys that you get two potential products. And I want you to come up with a mechanism that explains the formation of both potential products. So I'll give you guys a minute to work on this. You guys can talk with one another too. I'll give you guys another hint too. Don't make two identical products, right? They have to be different. All right, please make sure that you guys understand Chapter 9 chemistry at this point. We've got an alkene. We've got HBr. What's the first step? The pi bond's going to attack the proton, right? So this is exactly like what we saw in January. We'll attack this. We'll kick off our bromine. Where will the carbocation form? Will it form right there or right there? Green or blue? Blue, right? We always want to form our more stable carbocation, meaning it's going to come off the more substituted carbon. And what else is unique about this carbocation? Resonance. So if we look at the resonance structure for this, we can draw it like this. But what I'm going to do is I'm going to draw in our proton that was added in blue on both of these, and I'm going to bracket them in as resonance structures. All right, so we've got this resonance stabilized carbocation intermediate. Let's say I have bromine floating around. Bromine's now got two options for where it can attack. Right? It can attack this carbon, or it can attack that carbon. So let's draw our potential products from this. So this one could have the bromine attack from the top or the bottom, so I'll just write plus En. This one could have the bromine attack off of that less substituted carbon. And I'll draw in our blue proton. So technically there's actually three different products. You've got two stereoisomers and another constitutional isomer out of this. The question is, which one's more likely? The one on the left?
Yeah.
Okay, well, let's think about it a couple different ways. Imagine we protonate it, and you're the bromine ion. You want to go after the carbon that's closest to you, right? So if we look at this one, this bromine attacks closer carbon. So part of you could say, well, the one on the left is going to be more likely because that bromine's attacking the carbon that's closest to the area of the molecule where it installed that proton. However, what do you notice about the alkene? Which alkene is more stable? The second one. So part of us could say, well, the one on the left is more likely because the bromine's attacking the closest carbon. Another part of us could say, well, aren't we most likely going to form the most stable alkene? The answer is yes, for both. It really depends on the situation, right? Because this one, we've got the more stable alkene, and that will be our thermodynamic product. What do you think the one on the left is if the one on the right is our thermodynamic product? Kinetic, meaning it's going to be our most accessible product. It's going to be the one with that lowest activation energy. But let's also take a look at these two potential products.
So which one would react? Is the right one?
We'll come back. It depends a lot on temperature. So do you remember first term where I said we can control kinetic versus thermodynamic product formation based on temperature?
Yeah.
We're going to bring that topic back again. Yep.
So for this one, the carbocation is less important than the alkene bond.
Well, remember, the carbocation is being delocalized across two carbons. So part of us could say, well, the bromine just wants to attack the most accessible carbocation that's immediately available to it. And then the other part of our brain could say, no, we want to form the most stable product.
But in the actual solution, isn't there majority going to be the more stable carbocation?
It's kind of in between, right? So that positive charge, you're right. The major resonance contributor will be the one on the left. The minor one will be on the right. However, there's carbocationic character on both carbons. When we refer to these, we refer to the one on the left as 1,2 addition. Oop. We call this 1,2 addition because the bromine is installed on the carbon that's carbon 2, so one away from where our proton was. If we look at the other one, our proton's here, but our bromine was installed off of carbon 4. And so what we call this is 1,4 conjugate addition. We said that the 1,2 addition, at least in this case, is going to be our kinetic product. We said the one on the right will be our thermodynamic product. And if we want to favor the kinetic product, should we run this at high temperatures or low temperatures? Or we could look at the thermodynamic one. Let's say we just want to get to our most stable product and we don't care about activation energy at all. Best way to get there is just pedal to the metal, crank up the heat, get it as hot as possible, and it will favor going to the most stable product. So thermodynamic products are favored under high temp conditions. The kinetic product is favored at low temps. At least for this specific situation. Let's review the energy landscape. So you guys thought you got away from this. This is our reaction coordinate diagram. In this case, we had the same starting material. However, we had two different alkenes, right? So we had one alkene where the bromine came off the end. So let me finish drawing these. Then another one where, let me make sure I'm drawing this one correctly. We've got our bromine right here. Why is the di-substituted alkene more stable? meaning the one on the bottom. Does anybody remember? It started with an H. Hyperconjugation. So the di-substituted alkene, this one on the bottom, is more stable because it's got two different alkyl groups stabilizing that pi bond through hyperconjugation. The one on the top is only mono-substituted, so it's going to be a little less stable. The thermodynamic product, that bromine has to travel a greater distance in order to find its carbon, so it's going to have a relatively high activation energy. However, if we look at the mono-substituted bromine, the bromine's already right next to the carbon it needs to attack, so it's going to have a lower activation energy. So the thermodynamic product is always going to be your most stable alkene. That's the result of conjugate addition. Your kinetic product is always going to be 1,2 addition. Oops. Does that make sense? Okay, so let's do some practice. We're going to run this one in ice water, so 0 degrees Celsius. I consider that pretty cold. And then I want to figure out what product we get from this. Get started with our arrow pushing. Does it matter which pi bond we use? I picked the top one. No, it doesn't matter because it's symmetric. Where will our carbocation be? The tertiary position, right? We've got resonance because of the conjugation, which would move the carbocation over here. And then from each of these, we can get two different products. So let's draw both of these and then try to predict which one will be major and which one will be minor. Let me actually show some stereochemistry here. So we'd have this plus an enantiomer. And then for our other one, we would also end up with a mixture of enantiomers. Which one's going to be favored at 0 degrees Celsius?
One on the right?
One on the left, right? Because if we think about where we installed our proton, we installed this proton right here, and all of them. So the bromine is going to be right next to that carbocation location. It's going to be really easy to attack there. So this is 1,2 addition, and it's favored at low temperature. If we look at the one on the right, this would be 1,4 addition, and this would be our minor product. It's not going to be favored at low temperature conditions. What if I did want to favor the 1,4 addition? Just heat it up, right? Because if we look at this alkene for our thermodynamic product, it's our more stable alkene. It's tetrasubstituted. The one on the left is only tri-substituted. So if we did want to favor the 1,4 addition product, our thermodynamic product in this case, we would just crank the heat up. All right, let's do another practice one.
Explain one more time, what is the 1,2 mean?
1,2 just means that the bromine's installed one carbon away from the proton that was originally installed. If we look at the one on the right, it's 1, 2, 3, 4 carbons away.
How can we identify the group of proton? I mean, we can also choose another proton. I mean, what's the root?
So the blue proton, if we look at it color-coded, would be the proton that came from the HBr.
Okay.
So we're just looking at the relative position from that proton versus the bromine.
So our minor product is more stable.
Sometimes. It depends on the temperature. So with 1,2 addition, it will be favored at low temperatures, simply because the bromine's close to that carbocation center. If we want to favor the more substituted alkene, then we want to crank the temperature up.
But it's not always like that sometimes.
It's not always like that. You typically, 1,2 addition's always favored at low temperature, but your thermodynamic product may not always be your 1,4 addition product. All right, let's do another example one. This one's going to test your ability to draw a 7-membered ring. The least enjoyable ring to draw. All right, so we got 1, 2, 3, 4, 5, 6, 7. So that's a cycloheptene derivative. Now we're going to do the same thing. We're going to react it with HBr. However, this time we're going to crank the heat up. And I want us to predict the major product that will result from this. Nope, it's going to stay cyclic. Does it matter which pi bond we use? Okay, so I'll just pick one arbitrarily. I hate 7-membered rings. I apologize if this looks like a 3rd grader drew it, but because it's a cool problem. Oops. Oops, sorry. So the question is, will we get this carbocation or a different one? So this is our tertiary carbocation, but it doesn't have any resonance stabilization. So this won't be likely. Instead, we'll always favor our resonance stabilized carbocation, which if we were to draw it like this one's going to be much more favored.
What if you wrote low temperature? Wouldn't we put the left one favored?
Nope. Either way, you always want to go through your most stable carbocation intermediate, just like we saw in chapter 9. It doesn't always indicate that it's going to go onto a tertiary carbon. Resonance trumps a tertiary carbon. Not in the political sense. Nobody got a Trump joke there.
Can you explain again why we favor the one that's next to it instead of the tertiary carbon?
Resonance. So the intermediate I've got drawn on the right is stabilized via resonance. The one I crossed out has no resonance. Even though it's on a tertiary carbon, it's less stable than the one on the right because it doesn't have resonance. All right? So we've got these. Now we've got to predict our major product. Sorry, I have to scoot over. All right, so we've got bromine around for each of these. The question is, which one will be our major product? This bromine, if it attacks, could attack here. This bromine, if it attacks, will attack there. Okay, almost there. Sorry, I know this one's a pain to draw, but it proves a point, so bear with me. So, all right, so which one was our 1-2 addition product?
The top one.
Top one. So let's look at this. This is 1-2 addition. This is always going to be our kinetic product. The bottom one is going to be our 1-4 addition. Is our 1,4 addition our thermodynamic product?
Yes.
Is it? Let's look at our alkenes. Which alkene is more stable? The top one, right? If we look at the alkene in the top one, it's tri-substituted. The one in the bottom's di-substituted. So in this case, 1,2 addition leads to our kinetic product and thermodynamic product, right? So that's one tricky thing you've always got to watch out for is your 1,2 product will always be your kinetic product, but sometimes it will also be your thermodynamic product too. You have to look at the alkene itself. So in this case, this alkene is more substituted than the other option.
So will we get any of the bottom products at all? Or?
You might, but it would be very, 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 very improbable.
So the 1,2 addition is more stable here? Or-
Yes.
Okay.
Even though we're running it at high temperature, the kinetic product just happens to be our thermodynamic product. Do you guys want to look at the energy landscape to kind of take a picture of what's going on here?
Yes, please.
All right. So let's imagine we've got two different pathways. We've got our energy, we've got our reaction down here, we've got the same starting material for both of them, and we've got two different stability products. This one on the bottom was our kinetic plus thermo product. The one on the top, we'll just put a question mark. Kinetic product, how do we define our kinetic product? Lowest activation energy, right? So if we were to look at this one, we'd say, all right, this kinetic product has a low activation energy. And then the thermodynamic product means we form the product that is most stable, right? Our other potential route not only has a higher activation energy, but it forms a less stable product, which means it's going to be an incredibly unlikely pathway for this reaction to go through. Does that make sense? I'll give you guys a couple tricks to remember. 1,2 addition always gives the kinetic product because it has the lowest activation energy, and I'll call activation energy EA. 1,4 addition can give the thermodynamic product, but not always, kind of like we saw in the previous example. So 1,2 addition always gives you the kinetic product. 1,4 addition can give you the thermodynamic product, but not always. I always recommend drawing out both possible pathways. Your 1,2 product, label that as your kinetic right away, and then look at your alkene. The most substituted alkene will be your thermodynamic product. Sometimes that's 1,4, but not always. Does that make sense? It's a little bit tricky. And the problem of the day is looking specifically at these conjugate addition reactions. There will always be an option for a kinetic product. It just happens that sometimes you've got a separate kinetic and thermodynamic product. Other times they're the same thing. Yeah. All right. So now we're going to take a look at pericyclic reactions. They're a little bit odd, but they're a good introduction to the reaction that we're going to look at tomorrow. The first one we're looking at is called a cycloaddition reaction. And with a cycloaddition reaction, you start out with a diene, and you react it with another pi system. It can be either an alkene or an alkyne, and this is called a dienophile. That means that it loves the diene, right? And this will form a new bond between those two carbons. And then this pi bond will form a new bond between these two carbons. And then this pi bond will form a new pi bond between those two carbons. So this is called a pericyclic reaction because essentially you've got this cyclic flow of electrons and your product is going to be a cyclic ring, right?
So the pi bonds are constantly moving?
For this reaction, they're moving in a concerted manner. And if we look at it, those red dashes that I drew will now become covalent bonds. So these bonds are new. This is a new sigma bond. And then over here, we've got a new pi bond. So we've turned two sets of reagents into a cyclic ring with a new pi bond and two new sigma bonds in it. This is a very famous reaction called a Diels-Alder reaction, and tomorrow we're going to study this in a lot of detail, but I wanted to show you guys at least the elementary steps for it today. All right, the next pericyclic reaction we look at is electrocyclic. And with these, you have a conjugated system. So in this case, we've got a triene. And again, just like with our Diels-Alder reaction up above, we're going to get this cyclic flow of electrons. So this pi bond will hop down here. What do you think will happen with this pi bond? It'll break and go kind of clockwise all the way around the ring, just like we saw with the Diels-Alder. So this pi bond will hop over here, this pi bond will hop over here, and we've got the cyclic flow of electrons. This can only happen with conjugated systems, right? Because we have to have overlapping p orbitals in order for this sort of arrow pushing to occur. When we do these reactions, again, we've got a new cyclic system. We've got a new sigma bond. And we've got a new pi bond here and a new pi bond here.
Hey Jeff?
Yep.
When we're showing these arrows pushing, do we want to show it going to like a dotted imaginary sigma bond, or do you want to show it pushing to the next carbon?
You typically show it going in between the two carbons. I really like when I teach students to have them do the dotted line. That way they can visualize where the new sigma bond will form. Especially when we get into complicated Diels-Alder reactions, it's easy to mess it up. All right, so we've got this electrocyclic reaction. Again, we're forming a ring system. We've got a circular flow of electrons. The next one's pretty similar, and this is called a sigmatropic rearrangement. And with the sigmatropic rearrangement, it's really closely related to an electrocyclic reaction. However, instead of using a conjugated system, we've got an isolated system. So up here, this is conjugated. With the sigmatropic rearrangement, we've got a non-conjugated system. What do you guys think will happen with a sigmatropic rearrangement, just looking at the electrocyclic one? Let's try doing arrow pushing similar to our electrocyclic one. This pi bond can hop down. This pi bond can hop over. We don't have a pi bond next door, so what can we break instead? The sigma bond. So this sigma bond will hop over here. And let's try to predict what this product will look like. So we can break sigma bonds in reactions. We can't break sigma bonds with resonance structures. This isn't a resonance structure. This is a true reaction. So we are making and breaking sigma bonds.
So why you didn't break the sigma bond for the conjugate system? Instead,
Because we didn't have to, right?
you can just be bonds.
Well, let's look at the product of this one. This is kind of an unusual phenomenon. And you would look at this and you would say, all right, we've got this new sigma bond right here. We've got a new pi bond. And we've got a new pi bond. What do you notice about the starting material and product in this situation? They're the exact same thing, right? So with a sigmatropic rearrangement, at least in this example, you're just kind of flip-flopping your original molecule. The question is, how do we know that these reactions actually occur? Well, let's take an example. Let's say we've got that was a big sigh. Let's say we've got a fluorine here and a fluorine here. What will the result be from the sigmatropic rearrangement?
The double bond to be on 4 fluorine.
Yeah, exactly. So we could have a sigmatropic rearrangement where we basically flip it, but our fluorine's going to stay put, right? So sigmatropic rearrangements, you'll see them occasionally, but they essentially flip a molecule inside out in a strange way. So I think that's where we're going to leave it today. When we come back tomorrow, what we're going to do is we're going to take a very close look at the Diels-Alder reaction because it's one of the most synthetically useful reactions from this chapter. Yeah, there are a bunch of rules that can talk about that. We're not going to get into it too much. It depends on whether or not it's activated by heat or light. Yeah.